I am Anil Kumar. Welcome to my website, Global Math Institute. We are providing special services for students all over the world. You can contact me on email address anil.anilkhandelwal@gmail.com for guidance. Our series on integration is for students who want to understand the topic from very basics. Here is the fourth video in this particular series. We're trying to find area between the curves. We'll review in short what we have learned in earlier videos, and these concepts are going to be applied to find the area between the curves. So we'll review what was a fundamental theorem of calculus, its interpretation, and then take up examples to find area under the curve, area bounded in closed interval and the x-axis, and we'll see area between two curves. So let's begin with the basic concepts. Initially, we learned about the antiderivatives, and that was if f is a positive continuous function, important thing here is if x is a positive continuous function, then capital F of x can be interpreted as area under the graph of f from a to x, where x can vary between a and b, right? So rate of change of area is equal to the function itself when x is between the closed interval a and b. So from antiderivatives, you can actually get the area under the curve. So that gives you the link between derivatives and integrals. So a of x is basically the integral a to x of f of x d of x. Now Newton found, especially his teacher guided him to find a very good link between the derivatives and the integrals, that is linking gradient with area under the curve, and they came up with the fundamental theorem of calculus. It has two parts. In part 1, we discussed that if f is a continuous function on the closed interval ab, then the function capital F defined by integral of f of t dt between a and b closed interval. So what is to be noticed here is that the integral value really depends on the value of x, which is a moving boundary concept, right? And that is, if you're talking about a continuous function in a closed interval and the function is differentiable within the open interval a and b, in that case, antiderivative of f is capital F of x, right? Or you can say the derivative of capital F of x is f, right? Now, the fundamental theorem calculus part 2 gave us a mechanism of calculating this integral, and that says that if f is a continuous function on the closed interval a to b, then the integral from a to b, the definite integral between a and b of f of x dx is f of b minus f of a, right? So that is a very easy method of finding the integral itself. And now, if you make the connection from where we started to where we are, it gives you a connection between the area of the curve and its derivative. Perfect. We're going to exploit this in the video. Let's begin with example 1. Very simple. We've taken a straight line and we'll find the area under the curve. Example 1. Find the area of the shaded region shown under the curve f of x equals to 2x plus 1 from x equals to 1 to x equals to 2.5 bounded by the x-axis. So the region is shown right there above the x-axis under the curve between the closed interval where the points which we are considering are from x equals to 1 to x equals to 2.5. Now as we learn, straight away we can find definite integral between these two limits from 1 to 2.5 to get the area under the curve. So the function here is 2x plus 1. Derivative for this, the antiderivative for this will be x squared plus x interval 1 to 2.5, and you can evaluate this by substituting the value 2.5 first, right, and then 1, take away the difference, that is fb minus fa, right? So we did fb minus fa at this stage, and then we got the answer. Do you see how simple it is now? So that is how we use fundamental theorem of calculus to find area under the curve. So this is the basic concept. Earlier also we did this example with indefinite integrals, found the value of c, and then got the answer, right? Now this is much easier to do. Let's take up another example to explore this particular method. Example 2, we have taken a parabola. So in most of my videos, you'll find very basic functions. The idea here is to understand the concepts. Once you understand the concepts, you can easily solve any question, okay? Example 2, find the area of the shaded region shown under the curve f of x equals to 20 minus 3x squared. So that is the parabola opening downwards from x equals to minus 2 to plus 2, bounded by the x-axis. So we are considering when the graph is positive, and we are considering the area which is above the x-axis. It is all positive. Remember, integral could have positive or negative value, but area should be always positive. So in case we will see integral is negative, we have to consider the absolute value. Okay, so again, to find the area, we'll do definite integral of the function between the two limits. The function here is 20 minus 3x squared, whose integral is 20x minus x cubed. And from minus 2 to 2, when you plug in the values, what do you get? You get 32 minus 32, which is 64. So area under this curve is 64 square units. It is kind of important to understand that area is in unit square. And if no units are given, you have to write unit square as your units, right? So a statement saying that area of the shaded region is 64 square units is kind of important. Otherwise, at times, you might just lose 0.5 marks for not writing it. Okay. Now here is example 3. We'll now consider area between two curves. So again, we are strictly going with very simple examples, a parabola and a straight line. Nothing could be simpler than that, right? And the area is of this shaded region, which we need to find out. The question before us is example 3, which says, find the area enclosed by the function x squared plus 1 and g of x, which is x, between x equals to 1 and x equals to 3. Now, since we are looking into region between two functions, we should be developing a function which is f of x minus g of x, correct? So that will give us this particular area, right? You don't want the whole of it, correct? You have to take away that portion. So we are considering the function f of x minus g of x. F of x is x squared plus 1, g of x is minus x. So when you do that, you get the simplified function. Integral, definite integral between 1 and 3 gives you the area under the curve. So area in this particular case is x cubed over x plus x minus x squared over 2, and the boundary is between 1 and 3. So when you substitute the values, you find the difference fb minus f of a, and you can calculate this. The answer comes to 40 by 6, which is approximately 6.67. So now we can write down that the area enclosed by the region is 6.67 units. So I hope this concept is clear, right? So the important thing here is to find the function which is difference of these two, and then adopt the same method, which is fundamental law of calculus, right? So that is what we do, and property 2, which is fb minus fa, right, gives us the area. So that is the basic. Now let's move on and take another function. Well, this time you see that we are considering the part where the integral is negative also, right? So that is general type of question which you might get. So example 4 is find area enclosed by the function x cubed plus x squared and g of x equals to 2x. Diagram is given to you. We need to find the point of intersections. We are not given any points, right? So definitely we need to find points of intersection in this case, which you can see as these 3 points. But we need to find them, right? Now to find the solution, area is always positive. Find points of intersection and add the absolute value of the area between the curves. This is kind of important. Now, you could also do f of x minus g of x and g of x minus f of x, like interchange the functions to avoid getting negative answer. You could do that, but that is not necessary. Okay, so we have two functions here, the f of x, the cubic function, and then we have this g of x, which is a straight line. So as you can see, first step is to find the point of intersection. So the point of intersection is when f of x is equal to g of x. So you can equate and bring the terms to the same side, taking x as a common factor. Factoring the quadratic part, we get the x value as minus 2, 0, and 1. Substituting that into a simpler function, which is g of x equals to 2 of x, we get the points of intersection, which are minus 2, minus 4, 0, 0, and 1, 2. Perfect. Now it is a question of finding the area. So let's find area in two parts. So we'll find area of first region, we'll call this as A1, and then we'll find this area which we'll call as A2. So when you want to find area 1, we're looking into the interval from minus 2 to 0. And we already have a simplified version of f of x minus g of x, which is x cubed plus x squared minus 2x, right? So that is a simplified version. So we will integrate the same between the given limits. So the definite integral is as shown here. Now you can substitute the value. You can find what is f of 0 minus f of minus 2. And then you can find the value. So as you can clearly see, f of 0 is 0 minus everything else with x equals to minus 2. I mean, you get your answer, which is right there, right? So we get an integral which is 8 over 3, right? Since we kind of interchange, we wrote f on the top and g of x at the bottom. You understand, we got a positive integral. Now, for the second part, we have written this in the negative way. That is to say, instead of x cubed plus x squared minus 2x, you'll see I'll written negative values, which is minus 2x become 2x minus x squared minus x cubed. So I kind of wrote here as g of x minus f of x, right? But there is no need to do this. So that is the function which I have written here to avoid the negative answer primarily. Now the area we are interested in finding is between 0 to 1. When you integrate and substitute the values, area comes to 5 over 12. Total area is sum of these two areas, add them up and get your answer. Perfect. So that is how you could actually solve this question. So it really doesn't matter whether the curve is above the axis or below the axis, or it is just one curve. Even one curve, we're considering the x-axis as the other one, right? You understand? So that is how you should consider. So that gives us an insight to area between the curves. Now let's take more examples. This time we are complicating a bit. We're taking example where the function given to us is a cubic function and the other one is a quadratic function. The graph is shown to you right there. So it intersects at 3 points as shown. The question here, example 5 is, find the area enclosed by f of x equals to x cubed minus 3x squared plus 2x and g of x equals to x squared minus x. Again, we are not given the interval. So you need to find the points of intersection. That is key. So you need to find points of intersection. So first step is equate f of x to g of x. Once you do that, you can simplify and then this is a quadratic equation which can be factored. You can find the x values of point of intersection. So in this case we get them as x equals to 0, 1 and 3. Once you get that value, use the point equation which is simpler to find the point, which is 0, 0, 1, 0 and 3, 6. So these are the 3 points which are shown on the graph. Now again, we have to integrate definite integral between these intervals. So select each interval, right? So first, let us select the first interval which is between this, and then we'll select the other interval which is from here to there, correct? So that is how we are going to do it. So A1 is from 0 to 1. A1 is from 0 to 1, f of x minus d of x, and we already have an expression for f of x minus d of x, which, while you're finding the point of intersection, we kind of get this expression. So you could always use the same expression here to avoid rework and save some time. So that is your expression. So simple power function, apply the rules, get your answer, and when you calculate this, you get 5 over 12 as your answer. So we got A1, and now we can again use the same function to find A2, the area, which is between 1 to 3 this time, correct? So we use the same function and we found the area between 1 and 3, which came to negative 8 over 3, right? This time you see we did not flip f of x and g of x as we did last time. So as expected, we got a negative answer. Now, negative answer is not to be concerned. We can always take the absolute value. So the area is the sum of areas of absolute values. So add the absolute values and get your answer. Again, we got the answer as 37 over 12 units squared. So is this clear to you? Have a good look at what we did here. So first step in such questions will be to find the point of intersection. If there are 3 points of intersection, we have to calculate 2 integrals. And once you calculate these 2 integrals, then the area, absolute values should be added. Perfect. So it's kind of important to understand that the absolute values of the area should be added. Now that brings us to the last question, which is also examination style question. Here, example 6. Given graph of f of x equals to x to the power of 2 over 3 plus 1 minus 2 over x to the power of 1 over 3 and g of x equals to x minus 4. So these are the two graphs given to us. That is f of x. So let me write down here. This is f of x for us. And this one is g of x, straight line. Now, part A is find the x-intercepts of f of x and g of x. That means we have to find these 2 points. Part B is verify that C, which is 8, 4, is a point of intersection. So we have to verify that this point C is 8, 4. Part C is find the area of the region enclosed by f of x and g of x and the x-axis. That means we only want the area of this particular portion. X-axis and the curves in between the curves. Okay, so this is the area which we are interested in, right? So clearly, what should you do? So first step should be to find the area which is, let's say, A1, which is under the curve and the x-axis, correct? And then we have to take away the area 2 of the triangle. You see this area 2 is a triangle, so we have to take away area 2 of the triangle to get the area, which does not include this triangle. You get the idea, right? So this straight line forms a right triangle, and that is critical to understand. So in this right triangle, you can find that the side is between, once you find the x-intercepts, you know the sides, the legs, multiply them, and half of that will be the area of the triangle. So you have to take away area of the triangle from area of the first curve, f of x, and x-axis. Okay, so let's begin by finding the x-intercepts first. So x-intercepts, I adopted a method because this is radical functions, right? Solving radical equations will be difficult. So why not try some values? So we tried f of 1. If I substitute 1, I get 0. That means we have an x-intercept at 1. You get the idea, right? So that is how we tried it. Now g of x equals to x over 4. That is simple to answer. We are looking for this equation equals to 0. That clearly means that x is equals to 4, and so the point is 4, 0. So we get this point here at 4, 0, right? And the first point here as 1, 0. So those are the x-intercepts. Now we need to verify that 8 and 4 lies on both the curves. Point of intersection means both the curves. So let's find that also. Substitute 8 in your function. When I substitute 8 in the first function, what do I get? I get the value of 4. So that means this point is 8, 4 on the function f of x, correct? Now let's also substitute on g of x. When you do that, yes. So in g of x, when I substitute 8, 8 minus 4 is 4. So that means this point lies on the line also. And that surely means that this is the point of intersection, right? So it is common to both the curves f of x and g of x. Now, let's find the area. So in the first part, we'll find the area bounded by f of x and the x-axis. That is to say, the whole area, right? So we are going to find the whole area. Definite integral between 1 to 8 of the function, and this is your function, right? Power rule will be applied to get the value of the integral, and we'll evaluate the value within the interval 1 to 8. So once you substitute 8, so we do fb minus fa again, right? So that is fb minus fa, correct? So when you do that, you can evaluate the value. So substitute 8 and substitute 1, calculate the value, and what you get here is 83 over 5, or 16.6 in decimals. So that is the whole area, but we are only interested in the shaded region between the x-axis and the two curves, right? Not the triangle. So we'll take away the area of triangle. Area of triangle is half base into height. Now this is 4 units, since we know the other point is at 8, right? 8, 0. So the difference here is 4 and 4. Height is also 4, correct? So we get this area of the triangle as half of 4 times 4. That gives you 8. So we'll substitute 8 for the area of triangle, take away the value. And once we do that, we get the area of the shaded region, which is A1 minus A2. 16.6 minus 8 gives you 8.6 units square. I hope that is absolutely clear, right? So that is how you could solve questions where we have the area between the curves and the x-axis. So most of the time you'll end up with triangles, area which could be taken away, or sometimes you may have to do the combination of what we did in earlier examples. So I hope with this you understand how do we solve questions where we need to find area between the curves. Feel free to write a comment, share your views, and if you like and subscribe to my videos, that'd be good. And if you really want to learn from me, you can always send an email, send a request, and we are taking individuals for training, and we are also taking group classes. You could register for either of them. Thanks for your time, and all the best.